Okay, today we're going to be exploring, we're going into 3D. We need to break out our 3D glasses. So the key thing with 3D is again, what we're going to be doing is eventually going to equilibrium, right? And then we found that with equilibrium, there was two ways in two dimensions. We could use the little force triangle if we had three forces. But anything more than three forces, we were ending up going to rectangular coordinates and then setting all the x components equal to 0, all the y components to 0, and all the z components equal to 0. So same thing with our three-dimensional forces, is that we're going to have to break them up into these rectangular coordinates. So we've got a coordinate system here. No, this is not landscaping 101, so put your sprinkler here. So we have our x, y, and z coordinates. We'll have a force then that's described in terms of that space. So it'll be sticking out like that. And when we think about it, what we're going to be treating it is, or what we're going to be looking at is, we need to get it into these components. So we need to basically project it down here to the z. We need to project it to the y. We need to project it to the x. Now, there's one of the methods we're going to be talking about is called direction cosines, okay? Now, when you think about it, a cosine makes sense here. If I can direct it down here, if I know this angle here, basically the cosine of that. But the key thing to note is then the plane created by that force and that axis there, in this particular case the z, looks like that. So we see the horizontal there, but it doesn't relate to anything in terms of our rectangular system. It's not this plane, it's not this plane, it's not this plane. So it creates its own plane. And same thing when we look at the x coordinate. But again, I want that direction cosine. If I know this angle, I can still project it down onto that x. And then finally, the same thing with the y. But the key thing to note is that those angles are describing a plane that's created by the force and each of those coordinate systems. So when I say theta x, it will be this angle here. When I say theta y, it'll be this angle here. Theta z, it'll be this angle here. But the planes are completely different. They're not related unless, of course, the force is exactly on the xy plane or the zy plane or something like that. But in general, they create its own plane with the force and that axis system. And you can come up and look at this later if you want. You can touch it, feel it. So the three ways that we talk about this, just what we talked about, those direction cosines. Now what we'll find is all of the coordinate system, all the ways that we talk about moving it into rectangular coordinates basically create direction cosine. So the direction cosine is going to be the common thing between all three of them. And a matter of fact, when you get into doing your computer programs, matrix methods, finite elements and that sort of thing, this is how it stores forces. It stores it in terms of direction cosines and a magnitude. The other possibility is that we like to measure things in terms of a rectangular coordinate system. We know what y is, and we can form an x and a z or something like that. So we're very comfortable, especially when you think of like guide towers and stuff like that. We can get down there on the anchor of the guy, a particular guy, and measure the angle between it and the surface and that, and then measure it in terms of some sort of a horizontal angle. So if we have two rectangular angles known, we'll be able to describe it in terms of, we'll be able to get that force in terms of rectangular coordinates. And the one you'll probably see the most is 2 points on a line of action. So that basically means, like when we think of the guide tower again, I know the anchor point, and if I can measure where that point is up on the tower, I've got 2 points. I can use that then basically to break it up into our coordinate system, into a rectangular coordinate system. Okay, so we're going to introduce yet another unit vector. And again, a unit vector is dimensionless. It's a value of 1, but it's pointing in the direction of that particular axis system there. So again, we have a force. We'll set the origin there, basically at the tip of the force there where it's applied. And what we're going to find is that we're going to be able to then, as we did in 2 dimensions, we're going to use our little bookkeeping tool of these unit vectors, the I, J's, and K's. So our F now can be described in terms of these scalars times those unit vectors. So again, scalar direction, scalar direction. So again, a force is going to be composed of those 2 particular pieces that we need to know. Oh, I forgot to get the handouts going too. Gotten this done earlier, but now we got everybody in the class. Make sure everybody gets one, please. We'll dive into those in a little bit. Okay, first of all, direction cosines. And again, note, we said this is going to be common between all of the methods that we're going to do, but basically, again, it's a method of getting us into x and y, z components. Okay, so basically what we have here is we're going to describe our force again in terms of a magnitude and direction. Our direction is placed in here now. So our magnitude's out here, one unknown there, and then we have this direction piece here, which is going to be describing the contribution. Now remember, cosine doesn't get any greater than 1 and goes to 0, so it's going to be between 0 and 1. We'll be describing the component of that f in the x direction, the y direction, and the z direction. And those angles, again, remember, are it's that separate, that's a little plane there now that's created between F and then that axis. Now the one nice thing we can do with that, once we get things in terms of coordinate, or in terms of these direction cosines then, is we can describe a unit vector in the direction of our f. And basically, it's just going to be that interior piece there. This interior piece here basically is just a unit vector. Now, because it's a unit vector, the nice thing is lambda we know is equal to 1. And if I consider my Pythagorean theorem, basically I can describe my cosines. Now notice I'm squaring the cosines, I'm not squaring the angles here. So if I take this square, this Pythagorean's theorem, basically, squaring each of those. Now I don't have to do the square root because the square root of 1 is 1, right? So no issue there. But the important thing to note is since it's equal to 1, it's a unit vector, since that's going to be equal to 1, if I know 2 of the angles, then I can solve for the third. So when we think about it, what we're going to be doing then is taking that magnitude of f, if we multiply it times its cosine, and the other thing we can do then is, if I'm not looking for the component, if I'm looking for the direction cosine, if I know f of x and I know the magnitude f, I can find the angle by simply using the inverse cosine. And same thing with each of the other pieces there. So if I know one of those components and I know the magnitude of that, I can go back and actually start calculating angles. And then finally, if I've got the components and I've been asked to find the f, which is oftentimes an important thing, we might be designing some sort of connection there where we need to make sure it can handle the full force. We don't necessarily want the x and y and z components. Everybody got one? And again, just like we did in 2 dimensions, what we're going to be doing is creating resultants. And then when we get into equilibrium, we're going to set that resultant equal to 0. But basically, we need to sum up all those forces, and the way we're going to do it is via those components. Why we want to go there. And so on and so forth. So basically, it's just simply taking each of those. We're going to break every one of those forces into components. And what we'll see then in equilibrium is we're going to be setting each of those components, like we did in 2 dimensions, equal to 0. Okay, so we'll go to the balloon problem. So grab your handout and take a read of that, since we can't post it up on the board yet. Okay, so we got a balloon. This is going to be our case of 2 angles. So that'll be our number 2 method. So what we're going to do is, this is a typical application. We've been given a balloon that's got a tether on it of 800 pounds. It's trying to pull that little pickup truck down there. And we've been given a couple of rectangular angles. The first one, OB, which is going to be the direction of the pull that the pickup is seeing there. Basically, it's going to be 45 degrees with respect to the ground. So we've got it with respect to that XZ surface there. And then finally, we have X and Z, which now is on the ground in some sort of arbitrary directions. We might pick north and east or something like that, or something that we can easily relate it to. And we've been given the angle there between the Z-axis and OA as 60 degrees. Now notice that OA is not OB. It's the projection of that down onto the surface there. So we have to be a little careful. This isn't direction cosines at this point. This is 2 rectangular angles, which is the sort of thing we're going to actually be measuring in the field. So we'll just kind of draw our figure. One thing I'll note too is be careful. I tend to draw X, Y, and Z this way, but when you do a problem, when you're looking at a homework problem, you're doing the EIT exam, any sort of quizzes, look at the axis system and make sure you get it right, okay? Because I'll check it and give you partial credit if you get your X and the Y's mixed up and stuff like that. EIT exam, you get 0. So pay attention to how they got this. So if they say I want the X component of something, figure out where the X is. It isn't always in the way I draw it. Okay, so now we've got this tether. It's creating this force. What was it, 800 newtons? Like so. Okay, so now we need to think about what we want to do to get into the X, Y, and Z, but we need to think about what it is we know. So in terms of angles, we've got an angle measured from the ground, which is now our XZ plane, up to the level of the. So what we're going to do is now project that down to the ground. And note we were given that angle is 45 degrees. So basically think about it, if the sun was directly overhead, what we're going to see is our cable on the ground like that with respect to the coordinate system X and Z. Can you guys see that? X and Z as I've shown it here. And we've set that up some arbitrary. And then I've noted then, in terms of the force components, this is going to be Fxz. So it's not X and it's not Z. It's a component of both. And then I can also project it over and note, in that particular case, that is the y component. So it's a plane out like so. It's off at this angle, but when I move it cosine that way, or sine, depending on how you look at it, it'll be the Fy. This one will now be in the XZ plane and not completely what we need. So what we need then is to project that, noting that that's 60 degrees. And And what we'll see then is then we'll take that xz that we've projected now down onto the ground. We've got that measured angle of 60 degrees based upon some coordinate system I set up on the ground, an x and a z system. And then I can take that and move that fxz into a z component and then into an x component. So basically putting it into numbers, and I'll report it in terms of 3 digits. And then I'm going to get that projection on the xz surface by just simply doing, I don't even need to write that out, it's just going to be the cosine of that. Now I'm going to leave that with a number of digits there because that's not a number I'm reporting. It's a number I'm going to use on an interior calculation. So again, that's just simply our projection onto that. And then our next step is just simply now taking that piece and then I'll see that my projection in terms of what I'm going to report will be 490 in that x direction, and then fz will just simply be the cosine of that. So if I want to report that, then what I'll do is report it at no more than 3 or 4 digits of precision there. But I tend to want to keep those bigger numbers around because if I go into an equilibrium equation, I'm going to want to use a few more significant digits because, again, they're interior calculations. Again, I'm using 5 digits there. I come down here because I'm doing an additional calculation there. I carry the extra digits of precision in those interior calculations. When I get done reporting, I really can't report to anything more than 3 or 4 significant digits based upon all the wonderful assumptions that we make. Oh, question?
That f sub xz there, where did that fit in on your diagram?
This xz?
Yeah.
That's this projection down here on the ground. Notice it's right there?
Yeah.
Okay, so basically, again, it's not a component in our rectangular system. It's part of x and z, and we need that piece then to...
Yeah, I just labeled it OA.
Oh, sorry. Okay, so a lot of times we were given basically cables or something like that that are given to us in terms of a couple of rectangular angles and that sort of thing. Just be careful now what angles they give you, because a lot of times I've seen it, where they'll give you the angle from the vertical. Maybe it's 20 degrees there. So don't just arbitrarily apply sines and cosines. Think about, do I want the projection of the opposite leg or the adjacent leg? So think about that. Remember your geometry and your trigonometry and that sort of thing. Okay, that's our second piece. we'll go on to the next problem there. Which we're actually going to use in our equilibrium equation, and so it looks very similar to what we have in our third one, but I called this 212A. We've got a particular cable. So we're going to have 2 points on a line of action. So we're looking at that third method there. We've been given a guide tower there with dimensions in the x, y, and z directions there. And we've got a tension in the cable of AC, which goes from the top of the tower down to anchor there at C, of 920 pounds. And what we've been asked then to find out at A, what are the components of force at A contributed by that force AC. I'll bring all our pretty colors down here. A lot of what you'll see in statics and when you start getting into engineering is basically looking at three-dimensional stuff and trying to figure out how to express it in terms of 2 dimensions. So what we've got is a situation where we've got a point A up here. And we have a point C. So they're going to be basically 2 points of an anchor of a guide cable. Now, in reality, we know a guide cable is going to have some sort of a sag to it and stuff like that. But in our assumptions that we're going to be making is we're going to assume it's a straight line. And what we've got then is a tension in that, and we need to break it up into x and y components. And our information now, in this particular case, is simply going to be points in space. So we've got 90 feet there in the z direction. I have 30 feet in the x direction. Okay, so I'm going to lay it out in terms of 5 steps. In terms of your cheat sheets and that sort of thing for exams and stuff like that, I can highly recommend putting these steps in there. Just identify the steps. Okay, so we've been given 2 points in space, so we're going to be dealing right off the bat with some sort of lengths. And what we want to do is basically break it up into the length components because they're going to be related to the same as the force. So the pieces that we're interested in is this difference. And the difference is going to be, now again, you got to think about which direction you're pointing. So we know it's in tension, and if I'm up at A, that thing's going to want to pull me down towards C. So I know it's going in this direction here, so I'm going to define it in that direction. The way we define it in the direction is we're going to take the x component minus the a component, or the xc component minus the xa component. And what we'll see then is that what that's telling me then is if I want to get to that point C there, from A, I have to go 30 feet in that positive direction. Notice it'll end up in the positive direction. So think about it that way. Again, think about the traveling book that we did with the vectors and stuff. I'm doing it in space now. Same thing with the y component. And again, pay attention to signs. So my C is on the ground, where y is equal to 0. My A is up at 90 feet. And it makes sense. If I'm standing at A and I want to get to C, I don't want to go up 90 feet. I want to go down 90 feet. Think of it again in terms of motion. And then to get out in the z direction there, it's going to be 65 feet. And again, think about where you are at A. If I'm at A, which is basically along the origin there of x and z, it's going to take me 65 feet to get over there. OK, so step one, I'm just simply getting those length components. So I'm going and doing all those little differences. The next step is I'm going to calculate the length. And I'm going to use Pythagorean's theorem. Oh, hold it. Sorry. I'm jumping ahead here. That's step 3. Can't even read my own writing. Isn't too difficult. Basically, we're going to express it in terms of a vector now, in terms of our I, j, and k components. So AC will be this now. So it's just simply, we're expressing it in terms of our I, j, and k. It's an important step because then when we create our unit vector, we're going to use that vector. So basically, it's just saying to go from A to C, this is how far I have to go. It's expressed in feet. Now our length. Now, I'll note your author picks problems and numbers and that sort of thing, so everything comes out easy. Don't expect that on exams. But again, I'm just using Pythagorean's theorem. The length of that cable now is just simply 115 feet. But now I can use that to create my unit vector. And what I want is a unit vector in the direction of my force. And the way I do that is I'm just simply going to take this vector and divide it by the magnitude. You need to wake up to it. Maybe I'll take some of that too. Of course, you may not want me to talk that fast. OK, so what we're going to do is just simply take this vector and divide it by this length that we just calculated. And what we're going to find is that we're going to have it in terms of our direction cosines. So that's all we're going to do. And then again, since it's an interior calculation, when I plug it in, I'll either keep it as fractions until I need to actually calculate it, or I can work it out in terms of decimals. If we do it that way, we're going to add some extra digits. Now, a couple important things to think about here is again, since the magnitude is going to be the bigger number, all of these numbers should be less than 1. So if you don't have something that's less than 1, you plugged it in your calculator wrong. Sometimes it's easy to invert your division there. And the one way to check is basically the key thing is via that, what we've done is created the direction cosines. Okay? Because each of those, when you think about it, that's dx over d. Right? That's the x component over the total magnitude. That's the y component over the total magnitude. That's the z component. So what we've done is created our direction cosines. And the way we can check And one way to check then whether you got those correctly is it should be a unit vector. Basically, it says the magnitude should be 1. So we should get it in terms of close to 1, basically, in terms of our numerics. And then our final step, what we want is a force vector. We don't care about whether we have it in terms of how the length of the cable and that sort of thing. What we want is a force vector. But once we have the unit vector, then we have the ability to create our force vector. So force AC now is simply that magnitude AC times that unit vector. So then that allows us to take that 900 times that unit vector. So there's my FAC. There's my unit vector. And we can now express that force, that known force of 700 or 920 pounds, into its components in x, y, and z, and their proper directions. And the proper directions are going to be important then when we actually get into solving an equilibrium problem. Okay, so what we've done now is explored 3 different ways of getting a force into components. And the goal is again, equilibrium. So where we're going with this is we want to be able to create equilibrium equations just solving for unknowns. Actually, a very small section in your book, hardly any reading there. But again, basically, it's going to help us So again, what we're going to be doing is taking all these components and just simply adding them together. And in equilibrium, it requires that our resultant now is going to be equal to 0. So for my resultant to be equal to 0, I won't ask the question because you already know all the forces in the x direction have to be 0, all the forces in the y, each of these components has to be equal to 0. And what we'll see that's only different is we've added another equation, which means we can now solve for a third unknown. Because each of those is going to be a sum of some known and unknown forces, but the right-hand side of our equation is going to be equal to 0. If we get that 0, then we can start solving for stuff on the inside. Now again, this is for a set of forces that are all going to the same point. Guide tower is pretty nice and simple because all the forces are going through that single point. Okay, so 3D, the free body diagram, again, it's the two pieces that we're going to be using to solve for that. We're going to draw a free body diagram which will identify our forces and hopefully directions. And then we'll use our equilibrium equations. Now in this case, we're not going to be able to use force triangles. We're going to go directly to just simply setting those rectangular coordinates equal, or the rectangular pieces equal to 0 there. The not the coordinates, the components. Now, a couple ways you can show your and again, I make note when you're solving an equilibrium equation, if you don't have a free body diagram, you will lose points. So don't draw it on the picture that you have there because I can't see the forces and I don't know that you've identified the forces. One of the things we draw with a free body diagram, remember, is we're taking away things. We're taking it away from its supports. We're taking away other bodies and that sort of thing. So you have to draw a separate free body diagram in order to identify those forces. So three-dimensional drawings are typical. There's all my colors. Okay, so again, like the guide tower, we can just draw it in a three-dimensional sense there on a two-dimensional piece of paper there. So kind of have our x-axis going that way. We could have x and z at an angle and that sort of thing, however you're comfortable. But things you're going to need to put on it is a coordinate system. And the necessary coordinates. So basically, in this particular case, we've been given a set of directions in the coordinate, or distances in the coordinate directions there and that sort of thing. So we have that case where we're going to have 2 points, and we're going to have to use that in terms of calculating that unit vector and then finally the force vector. So one way to express it is that way. Some of you might be into CAD CAM and that sort of thing and want to look at things in terms of true 2-dimensional planes. So another possibility may be a little more difficult unless you're used to doing that. But our orthogonal projections basically says I'm only going to display what it looks like in a 2-dimensional plane. So using that same problem there, I didn't even identify that. We'll just call that P. So that's what it looks like in that particular plane. But then you need to draw all the other planes because you're going to need some other distances there. So then you draw that particular projection. So we're just looking at the xz plane. And then finally, oops, did I draw it? Yep. So again, it's just simply another way of expressing it. So if you're not comfortable doing 3-dimensional drawings and stuff like that, you can present it in terms of a series of 3 orthogonal projections, which is just simply your xy, your xz, and your yz. But again, the key thing is each one of those, even as a free body diagram, I have a coordinate system established, and I have dimensions on there. OK, so we'll dive into our next problem. And I saved you a lot of trouble there because I drew the free body diagram for you in a 3-dimensional sense. But again, it's the same problem. We've been given that tension AC, of which we've already solved in terms of components. But basically, it says now I need to think about, OK, what am I missing? Find out the other forces in the cables and in the tower itself. So when we look at that free body diagram, again, it's just a point. So recognizing that when I look at that point, I'm going to cut away those other cables. So I've got FAB and FAD, and they're shown a little more detail on your thing there. But the other thing, too, we sometimes tend to forget about it. We need to draw all the forces acting on that. And we recognize the fact that the tower itself has to keep that up there. Those cables are wanting to pull everything down. There's something that needs to react in the opposite sense there. So we've got our AC components. We just solved for those. The next step then is then I'm going to have to break each of these other forces into components. Now they're unknowns, but I can find those unit vectors. So remember, once I found that unit vector, the only unknown in that is just simply going to be the magnitude. So if I find the direction in terms of a unit vector of AB and AD, The only unknown is the magnitude on the cable there. And then P itself, that's a pretty easy direction to note there. But again, the only thing I don't know about that is going to be the magnitude. So we're going to go through the long, arduous process then of that 5-step process of getting myself in terms of finding FAB and FAD. Okay, so looking at the AB then, again, I'm going to be taking the x component at B. Now note B is out 45 feet, but it's 45 feet in the negative direction, remember? Notice my positive x direction is going the other way there, so it's going to be 45 in the negative direction. And then the A is, of course, centered right out there on the tower there, or the origin there of x and z. So again, think about it. To get out to C or out to B, then I would have to go in the x direction of minus 45. Same thing with the height. That's basically the same as what we did before there. It's going to be 90 down, basically. So it's got to be pointing down. And then the z direction there is going to be 30, but it's 30 in the positive direction. Notice that's in the positive sense there. So we have to be very, very careful with those signs. We've got 30, then again, minus the 0, we have it at 30. That's step 1. Step 2, I just expressed the chord. And that's actually in feet. So that's basically expressing the components of that particular cable AB in terms of its components. Next step then is coming up with a magnitude. And we get it in terms of 105 feet. Just a simple application of Pythagorean. My next step is my unit vector, which is just simply that AB vector over the magnitude. And again, a couple things to check yourself. A part of being an engineer is seeing whether the answer seems reasonable. Again, you can square each of those components and sum them. They should be around 1, basically, as a unit vector. But also, just look at the magnitudes. We notice in terms of y is going to be much bigger than the other two. As a matter of fact, it'll be I direction will be half of that, since it's 45 and stuff like that. So just kind of get comfortable looking at those magnitudes and make sure everything looks hunky-dory. And then finally, we're going to express it in terms of our force. This is what we want. And notice then, my only unknown is just going to be that magnitude piece. I've established the direction through my 5-step, 2 points known process. So my only unknown in this particular case then is that one. And what we're going to do is the same thing now. We've got to do the same thing for the AD. So my dx, let me pull up my picture there. OK, so A to D, my D is going to be, in terms of the x direction, a positive 20. So it's going to the positive 20 minus 0. So give me 20 feet. The y looks just exactly like the other one. And then we'll think about the z component is then it's going in the negative z direction. Our positive z is off to the left there. So that one now will have a minus component in front of it. First step, second step. Expressing it as a vector. And again, that's going to be in terms of feet. Next step, magnitude. I'm going to start getting lazy here, recognizing the fact that if I put a minus number there, if I'm going to square it, it's going to be positive anyway, so it doesn't really matter. And I find its length at 110. Then I create my unit vector now that I've got the magnitude and that sort of thing. And then I, again, express my force. And what I have essentially done, again, is I've created my direction. The only unknown now is going to be that. So I've identified two unknowns. Sir?
Why do you want it expressed in terms of the magnitude times the unit vector? Wouldn't it be more easier when solving for unknowns when you have just like the force in each component, I hat, j hat, and k hat, instead of the unit vector multiplied by the magnitude?
Well, that's what it is. When you think about it, see, another way we can express this is it's f AD times 0.1818 I hat plus f. Is this what you're asking?
Yeah.
Like this? Yeah, you can express it like that too. The key thing is it's the same f. It's the same unknown. The key thing is there's only one unknown in it. But yeah, you can express it that way if you want. Just be careful because the more you write things down, the easier it is to slip a B in there or a C or something like that. We know that in terms of, we try to reduce the writing as we can. But yes, there's no reason you can express it that way. See? Even the computer agreed. So you can break it up into those pieces like that, sure. Just like I say, be careful by the fact that that's only one unknown, though, in the whole thing. And that's why I like doing it this way, because we can pull it over there and say, look, the only thing I don't know is that.
Shouldn't the second term be a negative, though?
And it should have a negative term, yes. And that should be a negative term there, too. So we'll put that one up just to complete the thought. Make it look like that. So yeah, there's nothing wrong with doing that. You know, we're familiar with the associative law and stuff like that, so we can lay that out. Okay, now the really hard one, P. Do we need to go through the 5-step process? Which direction is it going in? Up. Okay, up. Just tell me in terms of coordinate system. Except for the y. So P and it's positive, right? Because the way I've shown it, at least, I've drawn it up. If I drew it down, that's fine. I can draw that. If I drew it down, I'd show it as negative, right? So in this particular case, I've got it going up in the same direction as the y direction, so I'm going to treat it as a positive. There are no components in the x or z, so it's just simply going to be my unit vector is just simply that j. And remember, j is our unit vector. Okay, so that leads me to equilibrium. What we need to do then is assemble all these pieces. We're going to sum all the x pieces, all the y pieces, all the z pieces, and we're going to set each of those pieces equal to 0, or each of those sums equal to 0. Okay, now I just kind of like laying it out on a table so I can kind of see what I have there. So I'm going to draw each of the equations and I'll number them. This is, actually it'll be my x equation, so we'll number them. Well, we'll number them in terms of 1. Okay, so I'm going to lay out a table. Let me set it up here for you so you can kind of see how we're going to do this. So we'll have 1, 2, 3, 4, 5 columns, maybe a 6th column there if you want to count the numbering system there too. And what we're going to do is just simply then go grab all those equations and look for the various pieces. So my AB piece will be that. So we just grab that out of that one equation. My second equation will be that, and it'll be positive. So again, I need to make sure I bring my signs along. Nothing under P. My AC, which we solved earlier there, and when we broke it up into three-dimensional components there. And then the key is that equilibrium requires that. Second equation. And again, I set my convention, my positive convention for my terms there. And what we're going to see is all of our cables are going to be in a negative sense. So I just simply go grab all of those particular components. In this case, don't forget the P. That's one of the things we're going to need. And then my third equation will be our Z. And again, I establish what my positive direction will be for that equation. And then I just simply grab all those pieces. And then I grab all of those particular pieces and plug it in, and notice that there isn't a P component there. So it's good to kind of lay it out in this form, because then you can kind of look and see how you want to tackle it. Now, if you have a matrix solver, very easy. You can plug it into a matrix solver like that. Can't do that on the exam, though, unfortunately. But I'm not interested in testing you on matrices and that sort of thing. So if I give you a complicated problem, it won't be horribly complicated. So what we'll do is, in this particular case, we'll just use a substitution method. And again, like I say, it's always worth just kind of looking at what you got here. And what we'll see is that our equation 1 and our equation 2 are both in terms of AB and AD only, and some known value. So what we can do is then and note then when we get into here, we can start plugging things in and start solving for one. We've got two unknowns here. So our key thing is we'll probably want to try to substitute for both of those in terms of P. So our substitution will set up our FAB. By just simply setting it on the other side of the 0 there, and then dividing through by the 0.4286. So that'll come up with a different term, and then my 240 will end up with another term there, and I add those extra digits along to carry along for precision. So I've expressed FAB now in terms of FAD. Now I can go into this one. Now that I've got that expressed in terms of that, I can go into this one now and start solving for something. I can plug now my FAB into this equation, which is now expressed in terms of FAD, and end up with an equation with one unknown. So laying what that looks like, and what I do is then take that 520 and plug it over on the other side there. It comes out as a minus. But just simply I'm plugging now this expression into here. Notice that I've got this in terms of, oops, that's supposed to be D. I've got it now in terms of one unknown. And then just simply plugging and chugging. Again, I keep the extra digits around, but when I report it, I'm just going to keep it down to that 3 or 4 digit level there. Now that I solve for FAD, I can go back here and solve for my FAB. So I return to 1. And then just simply plug that in there back into 1, and I can solve for that as 1240. Now that I've got AB and AD done, then I go back basically to my equation 2 there and solve for P. And again, noting that when I'm starting to plug those numbers in, I'm going back to my multiple digit ones, the ones that I don't want to report, but I want to plug those in because I've got an interior calculation here. I want to complete that. P then we solve for that. So nothing particularly tricky. Again, if you've got a matrix solver, I'd solve it that way too. Try to solve it 2 or 3 different ways. Get real comfortable with it in terms of solving it.